Physical quanta in quasi-crystals. This paper was given to the Global Summit at Anaheim in March. It's about quasi-crystals, it's about new data in quasi-crystals, which define physical quanta and defines it as a resonant response. I have to begin by explaining the difference between crystals and quasi-crystals. In a crystal, a periodic probe scatters off a periodic crystal to produce a periodic diffraction pattern. It obeys Bragg's law, n lambda equals 2d sine theta. N is integral. 0, 1, 2, 3, 4, 5, 6. In this instance, odd orders are suppressed by structure factors. We'll come back to that. The quasi-crystal is completely different. We have a periodic probe, we have a hierarchic structure, and a geometric diffraction pattern, where the order tau is irrational, not linear. And here's tau 0, 1 over tau, 1, tau, tau squared, tau cubed. And this has the additional property that the unit width of the unit cell stretches to tau squared in the icosahedral cluster, and in the icosahedral supercluster, tau to the power 4. The diffraction pattern is icosahedral, and the principal axes of this icosahedral structure are shown in the stereogram, and normal to the principal axes are the principal diffraction planes. They're all three-dimensional, geometric, simple, complete, and irrational. How does it diffract? We have to consider diffraction mechanism for the crystal and the quasi-crystal. Look at the red rays. The difference in path length is lambda. And in second order, the green rays, 2 lambda. And the wavefront is planar coherent. The interplanar spacings in the crystal are unique for any particular diffraction beam. That's the crystal. What about the quasi-crystal? It has multiple interplanar spacings. And the wavefront is higgledy-piggledy. It shouldn't diffract at all, but it does. How do we understand it? We can't use Bragg's law and apply. But we can use the structure factor method. What's that? We project each atom in a unit cell onto a selected plane, normal, sum the cosine phase, and that's how we got those forbidden lines in the crystal diffraction pattern that we looked at before. For the quasi-crystal, we made 2 adjustments. First of all, because of the higgledy-piggledy wavefront, we include a coherence factor. We don't know what that is to start with, but we're going to analyze it comprehensively and find its extraordinary properties. And secondly, because our unit cell is not periodically repeating, we have to sum over the whole crystal, and we do this iteratively using the stretching factor. And what's the result? The result is there's no Bragg diffraction. If there were Bragg diffraction, it would occur on the ordinate axis. But when we scan numerically CS, the quasi-Bragg peak pops up, and it turns out to be very coherent and diverges from the Bragg condition by this coherence factor. And the important property is that this coherence factor is the same for all the beams, hundreds of them, in the original data. How does that happen? Well, CS turns out to be identical for all the beams by means of a scattering factor in Euler's wave, and this produces the divergence from the Bragg condition. And knowing CS, we can measure the quasi-lattice parameter. And we find that it's the same as the diameter of aluminum, as it should be and has to be, and verifies both the structure and the method. So it's experimentally verified. But now I'm going to change gear. I'm going to convert from parallel beam diffraction that we've been discussing so far to convergent beam diffraction. This is where we focus the electron probe down to a point on the specimen. And look, we get the same general diffraction pattern, 0, 1 over tau, 1, tau, tau squared. It's geometric. But inside these diverging circles, we find also a linear diffraction pattern. And they have telltale descriptions of what they are due to. This is not quasi-Bragg diffraction or Bragg diffraction. This is dynamical diffraction, where we find mirror images between pairs of beams. And all of these beams are paired in the zero order beam. So this is dynamical diffraction. It's understood very well indeed in crystals. It's mature science. And here we find it again in quasicrystals. We shouldn't be surprised, but we are a bit. Because how does it happen that we get both geometric diffraction and linear diffraction in the same specimen? Well, it has to be because of the quasi-Bloch wave. What is a Bloch wave? Look at the blue wave. It's commensurate in a crystal with a unit cell and with all unit cells periodically repeating. And we use this to produce a lattice images. That's in crystals. But the blue wave is incommensurate with the quasi-lattice quasi-lattice. But however, if we stretch the blue wave by the inverse of the Carrier-Harris factor, we get the quasi-Bloch wave, and this has the extraordinary property. It's commensurate with the quasi-lattice, both long range and about each lattice point short range. This has all the properties that we need to get the dual diffraction and dual resonance in the diffraction pattern. Notice we're discussing momentum resonances that occur in diffraction. But the consequences are the same for other resonances in energy, in spin, in mass, in charge, and so on. Before I go on, a little bit about the wave packet. This is derived from Maxwell's equations. Electric field in the vertical plane, magnetic field in the horizontal plane, out of phase by 90 degrees. Two velocities, a group velocity and a phase velocity. In light, the two velocities are the same, but in mass, the group velocity is less than the phase velocity. And the uncertainty is the full width half maximum irritus when the horizontal axis is time. But if we do a Fourier transform with the uncertainty in angular frequency, it's the inverse. And the product d tau by d omega is equal to 8. This is 16 times greater than Heisenberg's uncertainty limit. Fresnel knew 100 years before Heisinger the uncertainty limit is the interface between near field and far field diffraction. And this has been verified by X-ray lithography at the critical condition. It corresponds to the extremum in Cornu spiral. But we need to go on to understand what is the group velocity and the phase velocity. We start with classical mechanics. Wave mechanics, velocity is frequency times wavelength. The same as omega over k. Relativity, and E equals mc squared, which is momentum squared plus rest mass squared. Quantization, which we'll return to. E is h omega, Planck's law. P is hk, de Broglie's hypothesis. Substituting, we find that omega squared is k squared plus m squared. Differentiating, omega over k multiplied by the derivative d omega by dk is c squared is very important. What's omega over k? That's the phase velocity. And what's d omega by dk? I'm going to show you that's the group velocity. the first sum perspective, Newtonian dynamics. Velocity is the square root of E over 2m. And in relativity, the velocity tends to c. The phase velocity is faster than c, and at the inverse of the group velocity. The mass is a constant m0 in Newtonian mechanics, but it varies in relativity. And the speed of light, the energy, is proportional to momentum. I'm going to leave you to do the details, but the way you convert from classical to relativistic is to replace Newton's rest mass energy with Einstein's relativistic energy. Here's the rest mass, here's the energy, plus the gun energy, here's the momentum, here's a wavelength, here's a frequency. These are experimental values. Here's the rest mass, and it divides the relativistic dynamics from the non-relativistic, faster than light, and the group velocity is slower than light, as Einstein had it. So what is the phase velocity? In Minkowski space, which is four-dimensional, time in the vertical axis, propagation direction horizontally, transverse phase front and back. And the significance is that if you have a charged particle at the origin, it can interact with another charged particle if it lies inside the cone, but not if it's beyond the horizon. And the cone for the phase velocity is much larger. The simplicity is at highly relativistic energies, the green and the blue overlap with the light cone. But at other energies in the electron microscope, we can use the phase velocity to understand magnetism, superconductivity, entanglement, and other features of physics. But we return to the original data. How can we get a system which is diffractive in geometric space and linear space from one specimen? And what we find is that the diffraction is dual in quasi-physics. Geometric and periodic, quasi-Bragg and dynamical diffraction. The quantum is a resonant response, and we have no other way of understanding this data without the resonant response. Finally, physics is falsifiable and explanatory. Axioms are math because they are unfalsifiable.